Thank you for tuning in to the 2021 Mineral Symposium of the Pacific Northwest chapter of the Friends of Mineralogy. This is our second virtual symposium due to the current health restrictions imposed by the ongoing global pandemic, so we're glad that you're able to join us here today. Our final speaker for the day is Leslie Moclock, who will take us out of Africa and bring us back to the Pacific Northwest. Leslie Moclock has a master's degree in geology from the University of California, Davis, where she taught field and laboratory geology. She held the position of curator at the Rice Northwest Museum of Rocks and Minerals in Hillsboro, Oregon for 5 years, where she enjoyed many opportunities to bring science to the public. And now here's Leslie Moclock discussing the newly released book that she co-authored along with Jacob Sealander, Rocks, Minerals, and Geology of the Pacific Northwest.
Thanks so much for having me here today. Thanks for the introduction, Julian, and thanks, of course, to the Pacific Northwest chapter of the Friends of Mineralogy for having me here. I'm really glad that you all are having your meeting virtually again this year, because that is allowing me to attend. After spending 6 wonderful years in Oregon, 5 of them as the curator at the Rice Museum, my family moved around a bit while my husband was finishing his medical training. And we have finally landed in Pennsylvania, in Lancaster, Pennsylvania. If you have ever been here, you've probably seen a horse and buggy or two. This is the land of the Amish people and shoe fly pie and cornfields and all of that stuff. But it's got a great little town too. And we are very happy to be here. And I've been keeping myself busy, volunteering a bit at the North Museum of Nature and Science, which is affiliated with the Franklin and Marshall College. They have some collection reorganization that needs a bit of a hand. But mostly what I've been spending my time doing is caring for my son, Rowan, who's now about 1.5 years old. And that takes about 27 hours a day. So it's a wonderful and joyful time of his life, but also a very exhausting one. Fortunately for me, he has already started to show an affinity for rocks, mostly by throwing them into ponds, but we're going to start somewhere and grow that interest as we go. But I'm here to you today to talk about my book, which was published just this past March. It is a field guide to the rocks, minerals, and geology of the Pacific Northwest, specifically Oregon and Washington. And it was a project that took about 3 years from conception to getting out on the shelf. And it started back when I was at the Rice Museum. The publishing house, Timber Press, was soliciting authors, basically asking for new authors to pitch ideas for field guides and other things in the sort of nature book category. And I thought, this sounds like a fantastic idea. If I get a contract to write a book, that means I will have an excuse to go out and do field trips to all the really cool places I've always wanted to go. And so I'm totally going to put my hat in the ring. And I was very fortunate that my proposal was selected to, for a contract and to go on to become this field guide. I didn't do it alone. I knew that taking on a project of this magnitude would benefit from some help. I asked one of my friends from graduate school, Jacob Sealander, to be a co-author on the project. He did his PhD where I did my master's at UC Davis, but he's originally from the Portland area. So he's the Northwest native of the two of us, which I thought would give us some street cred. And also he's a fantastic geologist in his own right. Furthermore, our interests and aptitudes were very complementary. So I did the rocks and minerals chapter. I looked at a lot of little details and discrete objects, and he did the structures and geomorphology chapter. So he did the sort of zoom out. Why is that mountain look funny? Why is there a river over there? And so between the two of us, we were able to look at the story of the geology in the region from different angles that fit together well. We did a lot of original photography for the book, both of us, and we sourced some photography. There were a few places I really wanted to get to that just didn't work out. So we have a few stock photos in there, tragically. But we did all of the illustrations and diagrams and maps and that kind of thing. So we got to do a lot of cool stuff to put this together. And I'm really excited to share it with you. So here we are looking at the front and back cover of the book. Lots of these images are probably very familiar to the people at this conference. We've got, of course, the painted hills on the front cover and some select minerals and rocks in the lower cover. But part of the reason that I wanted to show you the cover was actually to share with you just a silly little unintentional Easter egg. If you look at the back cover, it's a picture of an opal from Opal Butte. And, it looks really pretty. And it's from the collection at the Rice Museum. And this photo was chosen by the publisher for the back cover. We didn't, select it. But when I saw the mock-up of the back cover, I thought it was a fantastic choice, not only because it is a very beautiful specimen, but also because it looks maybe a little bit like the west coast of the US. You can see, here we've got Baja in California, and then we're coming up to Oregon. Here's the Columbia River. Here we go up into the Peninsula and Puget Sound and blah, blah, blah. So if you ever need a beautiful opalized, stylized map of the west coast of the US, here's where you can start off with. Anyway, all that aside, we're going to go through the book from pretty much from beginning to end, just to talk about what's in it and the thought process behind how it was put together, and specifically how you can use this book to get the information you want from it. Because we tried to put a lot of information from a number of different points of view and levels of interest in there. And so depending on what kind of reader you are or what you're interested in, you may find some parts more compelling than others. So let's look at the table of contents. We talked about how to use the book and an introduction to the topic of geology and the landscape of the Pacific Northwest. Then we have identification chapters for minerals and rocks, a couple of short interludes about meteorites and fossils. We have a chapter on structures and deformed rocks, a chapter on landscapes and geomorphology, and then a final chapter called Telling the Story, which is about the geologic history of the region. Also, you'll find in the end matter an appendix about field resources and where we got some of our data from and further reading. Very important, though, there's also a glossary. We worked really hard to figure out what level of language and vocabulary was appropriate for this book. One of the things that geologists love to do is make up words and then pretend that everybody needs to know what they are and why they're important. So we spent a lot of time trying to thread the needle between words that were specific and worth knowing and words that we could just not use and just use regular old plain English instead. But if we ever didn't quite hit the mark and you're like, what does that mean? You can always flip to the glossary to help you out. All right, so let's take a look at the beginning. This chapter could also be called everything you think you should know by now, but at this point you're too afraid to ask. So it's a lot of the big picture geology stuff, like what is plate tectonics anyway? How is the Earth put together, crust, mantle, core? What's the asthenosphere and the lithosphere? So it's got all of that sort of geology 101 background stuff. It's also got, of course, some diagrams about plate tectonics. Just as a quick note, some of these images like this one are a little bit blurry. And the reason is because I wanted in this presentation to show you screenshots of the actual layouts on the book page, and the file that I was given by the publisher with the actual layouts has some digital artifacts in it to prevent unauthorized sharing. But photos and images in the book itself are perfectly crisp. You know, it's not going to be a big deal in this presentation, but I just wanted to throw that out there. So back to this diagram, not only is it illustrating a number of very important topics in the model of plate tectonics, the theory of plate tectonics, and different kinds of boundaries like subduction and transform boundaries and spreading centers. But you'll notice it looks a lot like diagrams you've all seen of the plate tectonics of Oregon and Washington. And that's no coincidence. One of the reasons that the Pacific Northwest is such a cool place to look at and do geology is because it is like a living laboratory of active tectonics. You know, you look at all of the important features and concepts that you would learn about in an introductory geology class, and you can just drive around Oregon, Washington, and like tick them all off. Oh, there's that, there's that, there's that. Here it is. And that makes it a really exciting place to explore. You know, compare that to Kansas, which great state, lots of important stuff going on in Kansas. No active tectonics. You know, you're not going to find your volcano. You're not going to find your trench. You're not going to find your back arc spreading. Blah blah blah. So it's a very special place in the world to be, and one of the reasons that I was so excited to work on and write this book. So let's move on from plate tectonics. Again, in the realm of things you feel like you should know by now, but maybe you're too afraid to ask about. There's a short section on the geologic timescale with information about like where it comes from and why these sections have names and how they relate to the numbers and things like that. So this definitely falls in the category of this information that's here for you if you want it. If you couldn't care less, you could just flip on to the next page. We also set up the book by talking about the physiographic provinces of Oregon and Washington. There are, how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We have 13 provinces. And actually, I think 2 of them we decided were kind of the same one. So it's 12 provinces. And we refer to those later in the book. These provinces basically are areas that have similar geography, so similar vegetation, similar kinds of elevation, either flat or mountainous, and what kind of mountainous, similar kinds of climate, and that kind of thing. And they're areas that you've all driven through, you're all pretty familiar with. So, but we also have descriptions of those areas for those places you may never have been. So we have, for instance, some of the provinces here on the west sides of the states where you can see there's lots of water and big tall snow-capped mountains and trees and it's wet and pretty. And then you can go over to the eastern side of the state and you have another kind of pretty, the desert, more deserty side of the state, the exposed rocks where you can actually see the underlying rock formations and all of that cool, desolate stuff going on. So this is sort of an introduction to the region or to different areas if you haven't been to them. And then we head on to the identification chapters, starting with minerals. So minerals chapter starts off pretty standardly talking about the different physical properties that we use to identify minerals like habit and hardness and luster and streak and all that other good fun stuff. But there's also a section called finding crystals because a lot of the things that I put in this book came from many years of conversations that I had when I taught mineralogy as a graduate student. And then later when I was at the Rice Museum, one of the things that's really difficult for people to do is figure out whether they're looking at a crystal. You pick something off the ground and you have to figure out if it even is a mineral crystal before you can figure out what kind it is. And that first step can actually be surprisingly hard. to, when you pick up a rock, figure out what part of it is the crystals that you're supposed to be identifying. So this little section in here is an attempt to talk about that step. And I included it as an example of knowledge that I've absorbed in sort of the oral tradition of geologists, like things that are passed on from person to person, that I've never really seen written down in a textbook anywhere. And to make that kind of knowledge accessible to people who maybe aren't interested in learning geology in the classroom. So that's a little like secret cool thing for you. But once you've got a crystal in your hand and you know things about what is habit and what is hardness and so on and so forth, you can go on to the mineral identification process and understanding minerals. Now, this page has a lot of text on it, but we're going to look at some different sections more closely. The minerals in this chapter are organized by their chemical composition and physical structures. So we're starting out with the silicate minerals, which make up over 92% of the minerals in Earth's crust. So they're pretty important. You're gonna like stumble across a silicate mineral if you ever look at a rock in your life, and they are further subdivided by the different ways that their atoms sort of latch onto each other in these cool little tetrahedron. But if you pick up a rock, you pick up a mineral, and you look at it, you're not seeing the atoms, right? So like this actually might not seem useful to you. As you read the chapters, you'll see the ways that the invisible atomic structure is related to the bigger structures that you see in some minerals and the ways that minerals are related to each other. But this definitely falls into the category of information that's there if you want it, and if it makes your eyes glaze over, you can just cruise on right on past it. Something that's interesting as a unifying and organizing concept, but not critical to understand if you'd rather interact with minerals some other way. So let's turn to mineral entries themselves. We'll start with the feldspar group in the framework silicates category, and we're going to specifically look at plagioclase feldspar. So plagioclase feldspar is something every single one of you has absolutely held in your hand because it is the most common mineral in the Earth's crust and makes up about half of the Earth's crust. If you've ever picked up a rock and it had a white blob in it, and well, in the Northwest, chances are good that your white blob might be a zeolite. But if it's not a zeolite, it's going to be feldspar. And we talked about the ways that you can differentiate them. So I'm sure every single one of you has picked up a rock that looks like this one on the top right. It's got kind of a brown, gray, black ground mass, and then these blocky white crystals. The blocky white crystals are the feldspars. Or you might have a coarser grained rock where the feldspar is a little more globular. But these are all different examples of plagioclase feldspar. And so things that are common. So it was very important to us to include common minerals so that when you picked up a rock, you would be able to figure out what it was likely made of. But there's another reason that we care about plagioclase feldspar, because the gem variety of plagioclase is Oregon State Mineral, State Gem, the sunstone. And you can see it looks a lot different than this sort of little white, unremarkable blob. The sunstone is a feldspar that formed in a magma chamber where it grew very, very, very slowly over many hundreds of thousands, if not several million years. I can't remember the exact timeline at this moment. And it grew very, very slowly. So it was able to grow without messing up. Basically, it grew very perfectly, which allows it to be clear. And it also grew in the presence of copper. And the little bits of copper that sort of filled into the structure while the crystal was growing give it a beautiful yellow, rosy color. In some rare cases, even very deep red or very deep green. So this is, literally the world's most common mineral, that grew under very special conditions in Oregon to make this beautiful gemstone that so many people love and are captivated by, because it has so many cool qualities like schiller and the different colors and all that other good fun stuff. It's found in basalt. And I just think that's really cool that something so common can be so special in this area as well. We're going to move on to some other things that you'll see in this chapter. We'll look at agates, which are technically rocks. They're made of intergrown fibers of quartz and a mineral called mogonite. But we put it in the minerals section for sort of easy comparison to other similar materials. And these specimens are all specimens from the Rice Museum collection. You know, you could easily write a whole book about the agates in the Northwest, and people have, right? Because there are so many different varieties. It's very difficult to know what to choose. You know, you've got your banded agate and carnelian. You've got your plume. You've got your thunder eggs and your polka dot agate. So these are you know, things that are very beloved and captivating that are important to the region. And like I said, we wanted to be sure to include things that were both common and things that were interesting and rare and unique to the region. So there are over 600 species of minerals that can be found in Oregon and Washington, but there are only 62 that are in this field guide. And we chose some of them like clay, which you'll see over on the left-hand side, because again, it's very common, you know, but also interesting because clay is a mineral or clay minerals, when they get together and form a rock, are very good at preserving fossil impressions. So this picture, for instance, shows a paleosol, a fossil soil with root balls, little root filaments sticking out of it. So, you know, clay itself might not feel like a lot to write home about, but what the clay can contain and what it can tell us about the time when it formed is really cool. And then over on the other side of the page, we have a picture of pentagonite, standing in from pentagonite and cavensite. And those are type minerals in Oregon. They were first found in Oregon, even though many people are much more familiar with the bigger ones from India. But in Oregon in Oregon specifically, they're incredibly rare. There really are only a couple of localities where they're known, and one of them has been pretty much destroyed. So if you ever happen to stumble across one of these, you'll know that you found something super cool, and definitely to make a note of it and maybe collect some. And then again, for the super duper mineral nerds like me, it's also really neat that both of these are sheet silicates. They both have a similar underlying atomic structure, and one of them looks incredibly plain, and one of them looks incredibly beautiful. And it's just interesting to see the way that those variations can play out. There are a number of other minerals, some of which you'll be very familiar with, like of course gold, and others you may not have heard of. And at this point, you might be like, okay, I can see obviously there's a lot of very interesting information about how to identify these minerals and you know, the relationship of these minerals to the region and like why they're cool and stuff like that. But I can't pick up a rock and tell like what its atomic structure is. So how the heck do I actually use this book to identify a mineral that I'm holding in my hand? And the answer is you flip to this page. We have a couple of charts that list minerals by hardness and color and by habit and color. So if you pick up a mineral and it's green and it has an elongate habit and a hardness of where'd you go? 5 to 6. You can narrow down that that's probably actinolite. And if you can't narrow down what that is exactly, you can sort of use these charts to narrow down on 2 or 3 things, and then you can go read the mineral entry to get more information. So this is I have this thing in my hand. How the heck do I figure out what it is? Way to get you started to narrow down on the entries that you can then flip to and read more fully to confirm your ID. So it's the user-friendly part of the field guide. We're going to move on to the next chapter. Rocks. And rocks are, of course, aggregates of minerals. So we are moving up in the world in terms of scale. And we're going to find out what happens when minerals get together. I'm sure you are all familiar with the three major kinds of rocks: igneous, sedimentary, metamorphic, and the rock cycle, the way that rocks recycle themselves into other rocks. But again, this intro chapter falls into the category of things that you feel like you should know by now, but you're too afraid to ask. So feel free to read it in detail. And then we also have our generalized geological map of the region. And the generalized geological map highlights broad categories of rock types. So you can see that we have the igneous rocks in these warm colors: browns, oranges, reds; sedimentary rocks and sediments in blues and light yellow; metamorphic rocks in green; and some mixed groups also into the greeny purple. And if you look at this map and the way that these categories of rocks kind of, you can see they like stick together. Things that are similar are nearby each other, and they make these shapes that might look a little bit familiar. If you look back at the first chapter, it looks a lot like those physiographic provinces that we started out the book with. And that's not an accident. One of the reasons that each of the regions have their own set of physical characteristics, landscape and climate and other kind of characteristics, is related to the underlying bedrock geology and the processes that put those rocks where they are now, where they are today. So it's another cool thing about the region, that when you go from region to region, you're not just seeing different geography, but you're also delving into different processes and time periods in the history of how these states formed and became the landscape that we see today. I'll show you just a couple of the rock entries. Here we are starting with good old basalt. Not boring, in fact, very cool. There's quite a lot of it in Oregon and Washington. Very recognizable to anybody who's spent even 5 minutes looking at rocks, but has a lot of really neat stories. You know, the Columbia River flood basalts and Newberry and hotspot volcanoes and all of that good fun stuff is in here to learn about, and the landmarks that they make. But we do all kinds of rocks, including some that are a little bit more difficult to wrap your brain around. One of the things that people who are just learning to identify stuff have trouble with is separating color from identity. So it's very true that in both minerals and in rocks, there are things that are commonly one color or another. But very, very rarely can you use color as a definitive reason to make an identification. So for instance, this page spread is about a kind of rock called a tuff, a TUFF, a volcanic tuff. And if you look over on the left-hand side of the page, you can see that the top one is green and white, and the middle one is kind of beigey white tan, and then the bottom one is like pink, and it's got these black streaks in it. And these are all the same rock. These are all a kind of rock called a tuff. And so one of the main parts of this chapter teaches you to look at what are called rock textures, not just the colors of a rock or the shapes of the rock, but actually what are the textures of the components of the rock and how do they relate to one another. So tuffs are rocks that form from violent and explosive volcanic eruptions. So they're like the Mount St. Helens blew the lid off kind of eruption, and you've got the ash cloud and the pyroclastic cloud and all that other stuff. And basically, when you blow a bunch of rocks, you make a lot of fragments of rock, either from the country rock itself or the lava sort of spraying into the air and cooling really fast and all the gases and stuff. And then those particles come back to rest together, and they can solidify into a rock in one of a variety of ways. So that pyro, explosive clastic little pieces, sort of explosive little pieces texture is the thing that you use to identify a tuff, not a particular color or a particular shape necessarily. So this specific entry exemplifies that, but that process behind understanding and being able to see rock textures is the foundation for what this chapter is all about. And like the minerals chapter, the entries are arranged based on chemical and structural composition. But if you are holding a rock in your hand and you just want to know what the heck it is, you can flip to the end of the chapter where there are some flowcharts, where if you can start with what you think the texture is, you can then answer a series of yes or no questions that helps you narrow it down to a couple of different entries for something that it could be, and then you can read the entry further to help you make your more definitive identification. A couple of short interludes. There's the did I find a fossil and did I find a meteorite chapter. I included these because it's one of the most common questions when I got at the museum. People would bring in some weird rock and be like, is this a fossil? Is it a toe bone? Is it a skull? Is it an egg? And spoiler alert, rarely was it a fossil, sadly. Although sometimes it certainly was. So I don't know very much about paleontology or fossils beyond sort of being able to tell whether something is a fossil or not. So I can't like identify what your clamshell is or tell you what animal that bone came from, but I can tell whether something sort of is a fossil clam or a fossil bone or a piece of petrified wood. And so that's what this little interlude is about, and a similar thing with meteorites. So I'm going to pause here very briefly. We're going to, that was like a lot of information. Said a ton of things. We've actually gotten through most of the content of the book just from those first 3 chapters. And I know sometimes if we just kind of keep barreling on, a lot of the questions that you might have kind of get lost, or you're trying to wrap your head around something, and we blow by to the next thing. So we're just gonna kind of have a little Zen moment. All right, our Zen moment is done, and we're gonna do the last few chapters of the book. We're moving on to structures. So structures are what happen when rocks are acted on by tectonic forces, basically the ways that rocks are shaped by the forces inside the earth. We're actually only going to touch on this chapter briefly. This picture is of something called pencil cleavage, which happens when rocks are deforming in sort of a brittle fashion. They are higher up in the crust, and as they get pushed on, they break in a certain way. And this picture on the right-hand side is of a rock that was a little gooier when it deformed. It deformed in what's called a ductile fashion, kind of like silly putty. And you can see when it deformed, it made these cool sort of wiggly folds rather than a broken or shattered structure. And so we talk about those kinds of things: brittle structures, ductile structures, faults and folds. This, for instance, is a discussion of what a fault is. There's also a discussion of how earthquakes happen. What's the process of generating an earthquake, and how is that related to faults? We're actually going to move on really quickly to the landscapes chapter. This is possibly my favorite chapter in the book, even though I didn't write it. This was my co-author, Jake's chapter. And I mentioned at the beginning that we have complementary interests. And there are people who like geology because they like little things. Maurice Kelly, Julian Gray, little tiny things. And then there are people who like geology because they like big, gigantic things. And I like both. But when a lot of people are captivated by, as I said at the beginning, why is that mountain shaped that way? Why does this river look like this? What's up with this amazing coastline? And this is the chapter that looks at geology on that very biggest scale. So we started at the minerals, the teeny tiny scale. We went to rocks. We went to structures, which are sort of outcrop little features you can look at. And now we're at the big stuff, the landscape stuff. For example, I mentioned the coast. So the coast of Oregon and Washington is incredibly beautiful. It's really dramatic. It's got all kinds of topography and relief. It's got stacks. It's got arches. What are they? Where do they come from? This chapter talks about that. It talks about ways in which geology and geomorphology can have an effect on people's lives. So if you look at the top picture here, this is a picture of what's called soil creep. You'll notice that the trees are all bent at the bottom. all in the same direction. And this is an indication that this hillside is undergoing a very slow motion landslide. And we care about that kind of thing because if you were thinking about maybe, running away from it all and going to become a hermit in the woods and you wanted to find the perfect place to build your cabin, you would not build it here because it would eventually tear your foundation apart because the soil is slowly moving downhill. So that's the kind of thing that you would care about on the little time scale. And then on the bottom picture, this is a picture of the headscarp of a landslide that personally vexed me for an entire year because it kept me from my preferred commute home from work. I had to go down 26 instead of down 30, and it was very annoying. So this is a picture of the culprit, but it shows you, of course, what the aftermath of the fast-moving landslide can do. The reason that is relevant is self-evident in the photo. Looking more at a broader sort of history of the region in geology kind of way, we all know or have heard that the area in Oregon and Washington was glaciated during the last ice ages. There were alpine glaciers and some larger continental glaciers up in Washington. But how do we know that? And the answer is that we can see ways that these glaciers left scars on the landscape, both in the shapes of mountaintops, horns and cirques, and hanging valleys, and the scars of striations on individual rocks, the shape of these particular kinds of lakes called tarns. And so these kinds of observations will be able to give you clues to see the processes of landscape sculpting going on all around you. We talk about rivers, we talk about mountains, we talk about all kinds of cool stuff. Why certain rocks are round and certain rocks are pointy and all that good stuff. So this is a really fun chapter, and I highly recommend it. And that brings us to the very last chapter, telling the story. So I frequently like to say that rocks tell their own story. What rocks are made of, what they are, and where they are can tell you a lot about the history of how they were formed and sort of why that's interesting or why that matters. And so this book is an attempt to give you the tools that you need to be able to begin to read the story in a rock, to look and not just see a name for a rock, but also what that might signify in the bigger picture, grand scheme of things. And picking up a rock and looking at it is the most important thing a geologist can do. That's how you start to gather data. It's how you start to figure out what's interesting and what's not. But of course, geologists, also love their super fancy toys and their lasers and their microscopes and their analytical equipment and their mass specs and stuff. So there's a whole variety of other kinds of data sets that scientists have been working on for many decades that aren't necessarily readily available to the public, or not something that you can always access very easily on your own. So this final chapter is a little bit about the process of putting together your observations to tell a story about a rock that you're holding, but it also has the geologic history of the region, so you can, as it's sort of currently understood, still work in progress, so you can put your observations into the broader context of how this whole place came to be. So we have things that you are probably familiar with: terrain accretion, basically the train wreck of all of the island arcs and seamounts that got stuffed up against the subduction zone to make the landscape, the original landscape above the ocean of Oregon and Washington, the series of different periods of volcanism that followed, like this volcanism that's represented by the John Day area that's about 40 million years old, up until, of course, the recent volcanism of today. So we can see Mount Rainier, which is, of course, a currently active volcano. We can look at other ways that the region has been, instead of compressed, it was stretched out to make different extensional features like the basin and range faults that can still make earthquakes today. And they're also responsible for making the basin and range area in Southern Oregon with the super tall Steens Mountain and the very low Alvord Desert, and the ephemeral lakes that are there, and all sorts of other cool stuff that I don't have time to talk about right now. So this is the narrative part. This is the putting it all together part, and I hope you guys take a look and enjoy the book. Thanks so much for listening.